All right, let's do some physics. This is a problem that deals with energy loss / work done by an external force. We have a 0.28 kilogram wooden block attached to a spring on a flat surface with a coefficient of kinetic friction equal to 0.3. A force of 22 newtons then compresses that spring 0.18 meters. If the spring block system is then released from this point, how far beyond the equilibrium position will the spring stretch on its first maximum extension? Let's talk about what's going on here, frame our thinking, and then we can do some math. So these diagrams are kind of supposed to show what is going on. We start with everything chilling. Then this 22 Newton force compresses the spring 0.18 meters, and it is then released. If there was no friction, the spring in the block would move back and forth forever. Because there would just be a transfer of energy from spring potential energy to kinetic energy and so on and so forth forever. But because we have friction, friction is actually going to reduce the energy that the spring and the block possess. Friction is a kinetic energy killer. Friction converts energy into thermal energy. So energy is going to be leaving the spring block system in the form of thermal. This means that once the spring block system is initially released, the spring is not going to stretch 0.18 meters over here. It's not quite going to make it. We want to know how far it's actually going to go. I just want to define a bunch of things and kind of do the initial calculations in this box, and then we'll do the math for real. We will define E1, the initial energy, as the energy when the spring is compressed to 0.18 meters. And E2 will be the total energy when the spring is stretched. That's, basically we're looking for how far is the spring stretched when it's at the position E2. Because we have friction in this problem, energy is not going to be conserved. The initial energy stored in the spring does not equal the final energy that the spring has once it is maximally stretched. Friction is an external force doing work which allows energy to change. Work is always equal to change in energy, which is final energy minus initial. And I'm just going to rearrange this to say that the final energy that the spring has when it's maximally stretched is equal to the initial energy the spring block system possessed, added to the work done by friction. Work done by friction, work is always Fd cos theta. So the work done by friction would be the force of friction multiplied by the displacement over which it acts times the cosine of theta. Defining this d term is critical in this problem. The displacement over which friction acts. Friction acts across the original 0.18 meters that the block slides. When the system is released, the block slides the 0.18 meters back to its equilibrium position. And then it travels some new unknown distance that we're trying to find. But that new unknown distance from the equilibrium position to the maximum stretch length, that distance is equal to the stretch of the spring. So I'm going to rewrite D. The displacement over which friction acts is the original 0.18 meters plus the unknown distance that the spring is going to stretch. And I'm going to use the variable x here for change in length of the spring because that friction also acts over the same length. And I'm going to calculate some numeric values. So the force of friction in this problem is going to be 0.82 newtons. And we have spring force and stretch length values given in the problem. This will allow us to find our K, find our spring constant, which we are going to need. So I do some math, find the spring constant, get the spring constant to be 122.22 newtons per meter. And then I use that spring constant to find the initial energy. The initial energy of this system is all spring potential. So if I use the 1/2 kx squared, I can find out how much energy is stored in the spring or how much energy this problem starts with. Now that we've set all of that up, we can do the math for real. So I'm going to start with the expression that I have up here. I'm relating E1, E2, and the work done by friction. All right, the final energy possessed by the spring block system is equal to the energy it started with plus the work done by friction. And I'm just going to kind of start plugging in values. E2, once again, is going to be 1/2 kx squared, but we don't know what x is. That's what we're looking for. We found the initial energy value up above, and then work done by friction, I just plugged in Fd cos theta. Moving on, I'm going to keep substituting values into the work part of this equation. So the force is the force of friction. That displacement, right, the displacement over which friction acts is the 0.18 meters that it takes for the spring block system to go back to its initial position, added to that additional stretch length of the spring. And in this scenario, my cosine is going to be 180. Theta in a work problem is defined as the angle between force and displacement. In this scenario, the friction force is going opposite to the direction of motion, meaning that theta is going to be 180, or cosine theta is going to be -1. So I'm going to flip this plus sign to a minus sign. I plugged in the spring constant because we knew that, and then I plugged in the value for the force of friction, and I switched the plus sign to a minus sign because cosine 180 equals -1. And we're just going to kind of keep doing algebra, keep doing math to try and get x by itself. So the next step, the 1/2 times 122.22 becomes 61.11. I'm going to distribute this 0.82 into the equation. So we get 0.82 times 0.18 is 0.15, and then negative 0.82x. And I'm going to now move everything to get the x's on one side of the equation. So I add 0.82x to both sides to get all the x's on one side, and then the 1.98 minus 0.15 just becomes 1.83. One last little move to kind of get everything as clean as it can be. I need to solve this for x. How do I solve this for x? It's been way too long. Quadratic formula. When I plug this into the quadratic formula, I will get two answers. I will get that x is either negative 0.179 or 0.166. This negative 0.179 was where we started, right? We started compressed 0.18 meters, and then we're going to end stretched 0.166 meters. So that is my answer. Let's take the positive answer, and we find that the spring extends 0.166 meters.